while we wait for other people to arrive, let me go through the names I have here and see if you can guys communicate and speak in case you have a question. Antoine Dixon, are you there? Antoine, can you hear me? Can you answer to me?
Yes, I'm here. It's pronounced Antoinette, actually.
Antoinette. Oh, yes. I'm sorry. Thank you. Uh,
It's okay.
yeah. Jane Livatova.
Yeah, hi.
Hi, Jane. Joy Rizzolo. Joy Rizzolo. I think you may have been mute. You may have muted yourself because I see your microphone with a slash, which means that you need to change that if you want to answer. John Beck.
Yes, sir.
Hi, John.
Hello.
Hello. Joseph Martinez.
Yep, I'm
Joseph.
here.
Hi, Joseph. I can hear you as well. Joshua Meurer. Joshua, I think your microphone is mute also. Maxwell Sokol.
Hello.
Hello, Maxwell. Michael Williams.
Present.
How are you? Patrick Hall.
Hello.
Hello, Patrick. Reese Noss.
I'm here.
Hi, Reese. And Rhonda George.
Hello.
Hey, Rhonda. I think we had a couple of people joining. Amy Zimiti.
Hello.
Hi, Amy.
Hi.
And I think Ilan Lipsky also joined recently. Okay, I'll start with this presentation. We're going to be talking about chapter 1 of this class, and this class is being recorded in case you guys want to revisit or some of your classmates who couldn't make it can come. Please remember that we are going to be covering all the chapters along these 4 weeks. It's going to be different instructors each time. Some of the instructors will have more than a chapter. Some will have one, like myself, only this one. But you can attend to these online lectures and listen to all the chapters, which could be a very helpful thing. Well, we are going to be talking about fundamentals of physics, which is the name of this class. And physics is our explanation of how the universe works. It's obviously we are the title looks very impressive and pretending to know how things work in a very general context sounds daunting and almost impossible. So we are just going to touch the subject here and there. It's going to be basic knowledge, but it's going to be important nevertheless. So we're going to be talking about some laws and some equations that will help us understand the world we live in. And please, if you have any questions at any given time, just let me know. Well, physics applies to everything. As you can see in this slide, we have a picture of the solar system, we could say. It's not a picture, but an illustration rendering the solar system. And we have here an illustration showing a molecule with atoms. So we are talking about very large things and very small things at the same time. And obviously applies to all of us as well. Very small compared with the universe, but very large compared with the molecules. So the chapter 1 of the textbook that you should already have. It's about the patterns of motion and equilibrium. And so we will start by defining inertia. I listen a lot of background noise. If somebody is moving something around the microphone, would you mind muting your microphone so we don't hear all that noise? Thank you. We have to get used to how to use the system. A good idea could be to mute all the microphones and then if you are going to ask a question, you unmute it and then you ask a question. That would be a good way. So if you want to move or if you want to cough or drop something, it won't affect anybody. Okay. So an object in motion stays in motion unless acted upon by an outside force. And an object at rest stays at rest unless acted upon by an outside force. So what we are saying is for an object to change its state, for example, if it is moving or still, and we want to either change the direction or the velocity of the movement, or if the body is still, we want to have it move in any given direction, we need to apply a force. So an object that is still is not going to move by itself unless we apply a force. And that's kind of common sense. That's something we know in real life and we use it every day. We know very well that we need to apply a force if we want to move something. At the same time, if an object is moving and we want to change the direction of the movement or slow it down or accelerate that movement, we also need to apply a force. If we don't, the object will continue moving in the same direction. So the definition of inertia could also be that is the natural resistance of an object to change. So if we use some lines, for example, here is an object and that object is not moving, it's still. Now if I want that object to move and I apply a force, then the object is going to move. Another thing would be this object is moving and it's going to continue moving exactly the same way until I apply a force, in which case the movement is going to change direction, for example. That's because objects have inertia. This is kind of a silly joke about inertia, man. Because we all have an inertia, which is psychological too. Sometimes we take a time to move. We don't react immediately. And it's called inertia as well. Because we are sitting on the couch and somebody asks us to do something and we don't want to move. We have a resistance to movement. It's psychological, but in a way it relates very well with the physics concept of inertia. Now, how do we measure that inertia? Well, mass is the way to measure inertia. And mass is the amount of matter an object contains. It's not the volume, it's not the size, it's just how much matter, how much substance an object has. It could be very large or very small. It could have a more compressed substance or more expanded substance. It has nothing to do with that. It's just how much matter it has. So the greater mass, greater the inertia. The smaller the mass, the smaller the inertia. And we understand that in our everyday experience, because it is more difficult to move a very massive object than a very small object. So the more the mass, the harder, the more the inertia, and the harder it is to move the object. Somebody has a microphone on, and I can hear some. I don't know if it's a video or radio or TV or what. Would you mind muting your microphone?
Where's the mute button at? Sorry.
That's okay. It happens. It's kind of we need to get used to the system, and we are not used to it.
Okay. I can't find the mute. Could you tell me where it might be?
Yeah. Well, in my
I
interface,
found.
yeah, you found it. Great. Okay. Awesome. Now, another important concept is weight, and please be aware that weight and mass are not the same thing. We tend to confuse them. We tend to use them as the same thing. Even in real life, we use them as the same thing, but they are not the same thing. Okay. Mass is how much matter an object has. Weight is the force of attraction from Earth to that object. Uh, so, as this illustration here shows, the same astronaut on Earth has 120 kilogram mass, and on the moon has 100 kilogram mass. However, the weight on Earth would be roughly 1200 newtons. The weight on the moon would be 200 newtons. So the same mass is going to weight more on Earth than on the moon. So weight is something that depends on where we are in the universe. Mass does not depend on that. The mass is the same no matter where we are. So they are not the same. Now, mass is expressed in, in kilograms. Mass is expressed in kilograms. And weight, which is a force, is expressed in newtons. So two different units. So every time you see kilograms, you know you are talking about mass. Every time you see newtons, you are talking about a weight. Now, there is a relationship between weight and mass, and this equation here in this yellow square shows you that relationship. If you know the mass, you can find the weight by multiplying it by gravity. The acceleration of gravity, which, as you all know, is 9.8 meters per second square. So there is a close relationship between weight and mass. Now, what happened, and the confusion comes because in real life, we mix them. We say, oh, I weigh 200 pounds. Or we go to the supermarket, say, oh, I bought a pound of sugar. Well, when you bought a pound of sugar, what you are really buying is mass of sugar. But then we use pounds for the same, for mass and for weight. And the same happened with the kilogram. In some countries, they use kilogram as mass, but then they also have another unit called kilogram force, which is the unit of force. And then there is a big confusion. But please be aware, it's not the same. And each one of them has its own unit. So kilogram is the standard unit to measure mass. We are going to be using the metric system. So we are not going to work with pounds. We're going to work with kilograms here. On Earth, 1 kilogram of material weighs 9.8 newtons. So if I get an object that has a mass of 1 kilogram, I use the scale will show 9.8 newtons. And you could also check that by doing the calculation. Here we are multiplying 1 kilogram by 9.8, which is the acceleration of gravity, and the result is 9.8 newtons. Don't worry about the units. If the mass is in kilograms and the acceleration is in meters per second square, the weight is going to be in newtons. So it's a pretty simple problem. So what is the weight of a 750 kilogram object on Earth? So what do we have to do? Well, we have the 750 kilogram, which means we know the mass. And as we know very well, if we know the mass, we can find the weight, because the weight is going to be the mass multiplied by the acceleration of gravity, which is 9.8. So let's see how would be an organized way to proceed, especially for somebody who is becoming familiar with this. So let's see what we know. We know the mass and we know the gravity, because we are on Earth, as the problem states. So what do we need to find? Well, the question says, what is the weight? So we need to find the weight. Then, which equation we will find? On FSO, you have the equation sheets. You can download and print them, so you can have them to study. And then you look for an equation where you can find the weight, knowing the mass and the acceleration of gravity. That's a partial picture of the equation sheet, and that there is the equation W equal mg. So we say, okay, that's the one I want to use. Then we just plug in the values into that equation. 750 times 9.8. You don't have to put the units if you don't want, because as I said before, if the mass is in kilograms and the acceleration is in meters per second square, the weight is going to be in newtons, always. So you don't worry if you don't want, but if you prefer, go ahead and do it. Then you solve, multiply 750 times 9.8, and you get 7,350 newtons. So that is the weight of a 750 kilogram object. Now, just to make it more clear, let's compare mass and volume and see what is volume in relation with mass. Well, mass, as I said, is how much matter an object contains. If you have an object that you could compress, for example, you have a styrofoam, you have a block of styrofoam, you have a certain amount of mass. But if you compress that, because it's very easy to compress, you have a hydraulic press, you crush it down, it's going to become like paper. The volume is going to change dramatically, but the amount of mass is going to remain the same, because you didn't change the amount of matter. However, volume is just how much space the object occupies. So the block of styrofoam has a volume, let's say 1 cubic foot, if we are using feet as unit, or 1 cubic meter. But if we compress it, the volume is going to change. So the volume is just how much space that object occupies, regardless of how much mass it has. Now let's talk about scalars and vectors. And these are concepts, okay, that you need to have very clear, definitions. So we are also trying to build a language, a vocabulary, to speak the language of physics. Well, a scalar is a quantity that is completely specified by its magnitude. So we only need to know its magnitude. That's all we care about. For example, I have here in this bag a pound of sugar. So the magnitude is 1 pound. That's all I need to know. I don't care the size of the container. I don't care about the color of the sugar or the color of the bag. The only important information is the magnitude or the quantity of sugar. However, a vector not only needs a magnitude, it also needs a direction. For example, let's suppose this square frame you have here is a room, okay? And I am standing here where the red dot is. And I tell you, okay, I'm gonna move 3 meters. Let's suppose this is 3 meters, okay? 3 meters. I'm gonna move 3 meters. It is not possible for anybody to tell me after I move 3 meters where I am gonna be. Because I could be here, but I could also be here, or here, or here, or here. Any place that is 3 meters from where I am could be the solution. So I also need to specify the direction. So I could say, okay, I'm going to move 3 meters in this direction. Now I know that the only solution is this one. I will be there after I move 3 meters in that given direction. So this is an example. A displacement is an example of a quantity that not only needs magnitude but also direction. Another example. This is a box. This is a box on the floor. And I am going to apply a force on that box. I'm going to apply a force of 100 newtons. And as a consequence of that force, that box is going to move. Nobody can tell me in which direction the box is going to move unless I specify the direction of the force I am applying. So if I apply a force in this direction, this 100 newtons in this direction, the box is going to move exactly along that line. So now I know in which direction the box is moving. So a force needs to have not only magnitude, how intense the force is, but also direction. So force is a vector. Now in your textbook and most texts, uh, the vectors are uh, uh, expressed with a bold letters or with an arrow above them. For example, uh, if I have a, a regular number, which is a scalar, and I call it A, I will represent it this way. However, if it was a vector, I will represent it with a bold letter, or even better, I will put an arrow on top of it. So the A at the left is a scalar, the A at the right is a vector. These are the ways you can express a vector in when you write, or when you are reading a book. That's how you recognize they're talking about a vector or not. As you can read here, in Appendix C of your ebook, you can find more information about vectors. So force. Well, force is a vector. And the definition, before we go to the formula, let's talk about these definitions here. A force is a push or pull on an object. Yeah, you can push a cart, but you can also pull a cart. So that's the definition of force. Now, when you apply a force to an object, if there is nothing to resist or oppose your force, the object is gonna accelerate. So if you are on a very flat surface and you have a small cart and you apply a force to that cart, if the car doesn't have brakes and the wheels are properly oiled, the car is going to move. It's going to accelerate as you continue applying the force, and the car is going to move faster and faster and faster as you continue applying the force. Now, if there is no force, there is no acceleration. So if an object is still, for example, and continuous still, it means there are no forces applied to that object, or that all the forces applied to that object cancel each other. So if I have an object and I apply a force, the object will accelerate. Will move faster and faster. If I apply a force in a different direction, the object will move in a different direction. We already mentioned something about net force, but I didn't in a very explicit way define it. Because I said, well, if an object is still, it's not moving, it means there is no force applied to it, or all the forces applied to it combined cancel each other. I was talking about net force when I said that. What I meant to say is when the net force is zero. Because as you can see in this illustration, you could have two people applying a force. Let's suppose this gray block is a cart, and one person, John, is applying a force of 5 newtons, and Peter is a force of 5 newtons. Each one of them is applying 5 newtons. The net force is going to be the combined force of both forces, so it's going to be 10 newtons. So what matters is the net force, because most times you have more than one single force. Or for example, in this second block, John is pulling to the left with 5 newtons, and Peter is pulling to the right with 5 newtons. They are pulling in opposite direction. Therefore, the net force is zero, because both forces are the same, and in opposite directions, they cancel each other, and the net force is zero. And we know this by common sense, correct? It's like the tug of war. kind of situation where both groups are equally strong, nothing moves because the net force is 0. Sometimes we could be pulling, Peter is much stronger and is pulling 10 newtons to the right, and John is pulling 5 newtons to the left. The net force is going to be 5 newtons because it's always in the direction of the largest force, and the quantity is found by subtracting 10 minus 5 equal 5. So in that example, the net force is 5 newtons. And we could have many different situations. For example, we could have a block. One person is applying a force of 10 newtons, another one applying a force of 5 newtons, and I have here my little niece, she's applying 2 newtons. And on the other hand, we have a very strong guy, he is applying 14 newtons. Well, if I combine these three forces, the combine of these three forces is going to be 17 newtons. I still have only one force to the left. So the net force is going to be to the right. And, well, I don't have much space here, but the net force is going to be 3 newtons. It's going to be in the same direction of the largest force, and the number is 17 minus 14 equal 3. So 3 newtons is the net force. So the equilibrium rule, related with the net force again. The vector sum of forces. Of course, vectors can have any direction, and we only work in the examples of forces in the same direction, either to the right, to the left, but the same line. We didn't have force going up or down or going with an angle. The math for vectors is a little bit more complicated, so we are not going to go into those cases. But the same principles apply. But we are going to keep it simple, because what we want to work is with the main concepts, basically. So vector sum means all the forces, including the direction. So you could have a little different outcome depending on the situation. But what we did before was also a vector sum. It was a simpler one, but it was a vector sum. So if an object is in equilibrium, it means the object is not accelerating. That's the definition of equilibrium. Non-accelerating. It could be moving at constant speed, or it could be still and not move. In both cases could be equilibrium. If it is not accelerating, for those conditions to happen, we need that the sum of all the forces is 0. And that's the equilibrium rule. Now, this symbol is epsilon, is a Greek letter that is means sum of. So if I write this, it means the sum of all forces. But I could also say this, well, the sum of all cash. So you could use it for anything. It's just a symbol. It's just a way to simplify the writing. It's easier to write this symbol than to write the sum of every time. And in physics and math, it's customary to try to find simple expressions. And by using these symbols, it's much easier. So this here means the sum of all forces equals 0. And that's the equilibrium rule. When that happens, once more, there is no acceleration. And as a consequence, the object is either not moving or moving at constant speed. These two cases are when there is no acceleration and the net force is 0, once more. Now we have two kinds of equilibrium uh, that they relate with these two situations here. One when it is not moving and one when it is moving. So let's see how it goes. Static equilibrium is when it is not moving. For example, this book on the table. This book is in equilibrium because it has a weight that is pulling it down. Earth is attracting it, pulling it down. But there is a support force. The table is applying a force underneath the book, and that force is up, and it's the same as the weight. So the net force is 0. That book is in equilibrium, but because it is not moving, it is in static equilibrium. Now that support force is also called the normal force. Now for the dynamic equilibrium, we need to talk a little bit about something else, friction. So this is a box, and we are trying to move the box in this direction, but as we move it, there's going to be a friction between the box and the floor. There's going to be a friction trying to resist this movement. So friction is a force that acts in an opposite direction to movement. For example, I have two objects here, two bricks, for example, and they look like smooth and flat, but if we look with a microscope, the surfaces are not smooth. And as a consequence, there is a friction. Of course, depends on the material. If the materials are glass or very polished steel or aluminum or just concrete, the friction is going to be different, correct? So friction will depend on those small details of the surface. So how does dynamic equilibrium happen? Well, this girl is trying to move this box. So she applies a force of 75 newtons, for example. As a consequence, the box starts moving. But this is what happened. As the box starts moving, a friction force happens. That is going to be in the opposite direction of the movement, which is the same direction of the force. And as the box increases the speed, the friction increases. And there's going to be a time when both forces are exactly the same. The applied force is the same as the friction force, and the box is going to continue moving at constant velocity now. At the beginning, when the velocity was small, the friction force was smaller. Therefore, there was a net force in this direction and the box was accelerating. But the moment these two forces become equal, then the net force is zero and the box will continue moving at a constant speed. And that's what we call dynamic equilibrium. So it's an equilibrium of an object in movement. Another good example of this could be skydiving. You know, when you open your parachute, you're moving very fast the moment it opens. And the only force pulling you down is your weight. But as the parachute opens, because of the high velocity you have, there is going to be an air resistance pulling you up that is going to be bigger than your weight. So you are going to slow down until your weight equals the air resistance of the parachute, because it's going to slow down until they match each other. When that happens, you fall down at constant velocity until you hit ground. That's another example of dynamic equilibrium. So speed and velocity. Speed and velocity. Well, in general, velocity is a vector and speed is a scalar. For example, I could say, well, I'm traveling at 50 miles per hour. That could be my speed. As a fact, we talk about speed limit because the direction doesn't matter. I could go north, south, east, west. You know, I'm going to get a ticket by a police officer regardless of my direction. So I have a speed limit I need to watch. However, if you're traveling and I tell you, okay, I'm going to drive at 50 miles per hour for an hour, if you want to know where I'm going to end, I also need to specify a direction. So I will need to say, okay, I'm going to drive 50 miles per hour north. That's the velocity because it has a direction, because it's a vector. So, well, we have average speed. Because if I'm driving, for example, from Orlando to Tampa, if I travel from Orlando to Tampa, let's say I want to drive 100 miles and it's going to be 2 hours. So my average speed is going to be 50 miles per hour. Because what I do, the formula we'll use, velocity is distance divided by time. If my distance was 100 miles and my time was 2 hours, then my velocity would be 50 miles per hour. And I'm using different units just because these are familiar to you. However, you know very well that along those 2 hours you were driving, sometimes you were going faster Sometimes you were going slower. A big truck ahead of you, and you were forced to slow down, and then you accelerate because you wanted to pass the truck. So your velocity or your speed is everything but the same all the time. So this 50 mile per hour thing means my average speed. However, at any given time, I could look at my dashboard in my car and I see my speedometer. For example, while I'm passing the truck, I can see 75 miles per hour. Before I passed the truck, I was going at 55 miles per hour. So at the moment I watched my dashboard, I took a look at my speed in my dashboard. What I was talking about was my instantaneous speed, was the speed in that instant, which is going to change a couple of seconds later. But in that moment, I have a given speed. That's instantaneous speed. So here is the equation. Speed is distance over time. The same formula I used before. And here, there is a little bit of redundancy here. So yes, velocity is a vector. The speed is a scalar because only has magnitude. Uh, and there is a formula here that is it's the same basically as velocity distance over time. This quantity here, which is this one as well, they just mean distance. How I calculate the distance. So suppose I have a measuring tape, which we do as a fact, along I-4, along a highway. And how do I know how much I moved? Well, I could, at the side of the road, you have signs that tell you, oh, you are on mile 74. You are on mile 58. So let's suppose I'm driving and I say, okay, let me start checking right now. At the moment I say that, I am on mile 58. I am on mile 58. And then when I decide to check again, I am on mile 72. Well, 58 would be my X initial, like here in the formula. And 72 would be my X final, like here in the formula. So if I use the formula, I would do 72 minus 58, and whatever time, let's suppose it was 15 minutes, or let's say 15 minutes, which is 0.25 hours, quarter of an hour. Well, I divide that by 0.25. If you make that calculation, you get 56 miles per hour. So what I'm doing is using this expression here to calculate the distance by checking on this. It's like having a measuring tape along the highway. So it's just a different way to express the same. So let's solve this little problem. What is the velocity of a car that travels 150 meters east in 2 seconds? So I know the distance, I know the time. So I could say, well, velocity is distance divided by time. So it's going to be 150 divided by 2, 75. Sorry, I used the wrong M. Meters per second. And that's my velocity. I have to specify east because my direction. This formula is on the formula page. You can download from FSO as well, or in your textbook. So once more, following the steps, what do we know? The distance and the time. What do we need? The velocity. What equation are we going to use? That one in the formula sheet. Here is the formula. We plug in the values and we calculate the solution. 75 miles per hour. Well, motion is relative. This is a very important notion because right now I'm sitting on a chair. And if I ask you guys, what is my velocity? You all would say, oh, 0. You are not moving. Well, we are moving around the sun at this speed, 100,000 kilometers per hour. Okay? So we are moving very fast as we speak. And as a reference, so you can understand the magnitude of that, the shuttle travel up to 30,000 kilometers per hour. So the shuttle travels slower than Earth around the sun. So motion is relative. So when we talk, we always say, well, in relation with Earth. I mean, for most common things. Now, somebody working on NASA, they will obviously think differently because they are going to be talking about outside, and therefore they probably need to use more information. But for us here on the ground, that's plenty. Acceleration. Well, acceleration is the rate at which velocity changes with time. So when we apply a force to an object, the object accelerates. And that acceleration means that the velocity is changing along the time. A positive acceleration means that we are speeding up. A negative acceleration means we are slowing down. Zero acceleration means that the object is either sitting still or moving at a constant velocity. The units of acceleration are meters per second square, like the unit of velocity is meters per second and the unit of time is a second. This formula here is how you find the acceleration. The final velocity minus the initial velocity divided by time. If you look at this formula, final velocity minus initial velocity is nothing else but the change of velocity. So if you divide the change of velocity by the time, you obtain acceleration. For example, an object goes from rest to 50 meters per second in 10 seconds. What is the acceleration the object is experiencing? Well, the initial velocity is 0. From rest means the initial velocity is 0. 50 is the final velocity. So the change of velocity would be 50 minus 0. So the change of velocity was 50. in 10 seconds. So we apply this formula. Here, the change of velocity, final minus initial, 50 minus 0, divided by the time, which is 10 seconds. We obtain 5 meters per second square. You don't have to write the units all the time. You could just write the numbers and then put the unit at the end. So you could have said acceleration equal 50 minus 0 divided by 10 equal 50 divided by 10 equal 5, and then I put the units. Because I am calculating an acceleration, it has to be 5 meters per second square, and that would be good enough. Now, what does 5 meters per second square mean? It means that every second the velocity increases 5 meters per second. Every second the velocity increases 5 meters per second. So we start at still from rest. 1 second the velocity increase 5 meters per second. The second increase 5 meters per second additional more, and 5 more, and so on. When you get to 10 seconds, if you continue in this progression, when you get to 10 seconds, you will have 50 meters per second. That's what deceleration means. Another problem. A car traveling at 30 meters per second crashes into a wall and stops in 0.1 seconds. Well, the 30 meters per second is the initial velocity. Because it crashed into a wall, the final velocity is 0. Stopped. The wall stopped the car. So here you have 0 minus 30. The initial velocity is 30, the final is 0. Time is 0.1 seconds. When you make the calculations, you get minus 300 meters per second square. You get a negative acceleration because the car slowed down. It was a negative acceleration. And you can see here the same progression. How the speed decreases as time moves. Of course, here we have to use small fractions of a second because the stop was very sudden. Most likely at this speed, whoever was in the car will die, or at least the car will be completely destroyed. Now, if I drop an object, let's say I'm holding a baseball and I drop it, it's gonna fall. It's gonna fall. But it's gonna accelerate down. It's gonna fall increasingly faster, fall and faster and faster. The acceleration of any falling object on Earth, if we neglect air resistance, is gonna be 9.8 meters per second square. So you have a baseball, drop it, it's gonna fall, and the acceleration is gonna be 9.8 meters per second square. It means every second the velocity is going to be increasing by 9.8. That's what we call G, gravity. Of course, that gravity will change if we are in a different planet or in the moon, for example. This is how the speed will change. When I drop the object, after a second, it's going to be falling at 9.8 meters per second. After 2 seconds, increase 9.8 more is 19.6. After 3, increase 9.8 more is 29.4, and so on. Free fall. So an object is in free fall when there is no air resistance. That's a must condition for free fall. No air resistance. And the only acting force is the acceleration of gravity. So this guy is dropping the ball here. Every second the fall is going faster and faster. That's free fall. And you could see that. Oh, I think I went too far. Okay, here we are. So if we are doing animations, obviously we are going to see something like this baseball here. That is free fall. Okay. Suppose every picture of this baseball is one fraction of a second. The same fraction every time. Let's say 1/10 of a second. 1/10 of a second. The second tenth falls more. The third tenth falls even more, because the ball is accelerating as it falls. Okay, guys, this ends this training session for the chapter 1. I hope you got something from it. We basically ran out of time, but if you guys are willing to ask a question, I'm here for you guys.
I actually do have one.
Sure.
To be more accurate, shouldn't it be 9.81 meters per second squared instead of 9.8?
You're absolutely right. You could use 9.8. Well, that would be more accurate. Yes.
Okay.
It's very common to use 9.8, but of course, it depends on what we're doing here on Earth, and studying this mostly as a concept. That's good enough. But you're right. I mean, if I was working for NASA, I would like to use 10 decimals, but yes, you're absolutely right. 9.81 would be more precise. Thank you. Any other question? Well, if there are not more questions,